Ever wonder why some places on Earth are constantly bathed in sun, while others are perpetually shrouded in clouds? The answer lies in the fascinating world of pressure belts and atmospheric circulation, which are the keystones to understanding our planet's varied weather patterns. At the heart of this system is the uneven heating of the Earth by the sun. The sun doesn't distribute its warmth evenly across the globe. The equator receives a more direct hit than the poles. This disparity in solar heating creates zones of different air pressures across the planet, known as pressure belts. These belts in turn determine the general climate and weather patterns of an area. In our journey today, we'll delve into the specifics of these pressure belts and the associated atmospheric cells. The equatorial low-pressure belt, with the Hadley cell, the subtropical high-pressure belt, alongside the Ferrel cell, the subpolar low-pressure belt, and the frigid embrace of the polar cell. Understanding these belts and cells unlocks the mysteries of our planet's diverse climates. Right at the equator, the sun's heat is intense. But what does that do to the air? Well, let's dive into the equatorial low-pressure belt to find out. This belt stretches right along the equator, where the sun beats down the hardest. Here, the intense solar heating causes the air to warm up significantly. As this warm air heats, it becomes lighter and rises, creating an area of low pressure beneath it. This rising air doesn't just drift away quietly, it's the main reason behind the heavy rainfall and frequent thunderstorms experienced in these regions. Now, imagine this rising air as part of a larger atmospheric circulation known as the Hadley cell. In the Hadley cell, air rises at the equator and then travels towards the poles at high altitudes. Eventually, it cools and sinks at about 30 degrees latitude. This creates a loop of circulating air, which is crucial for distributing heat and moisture around the planet. So this constant movement creates what we know as the tropical rainforests and deserts. Moving on, as we move away from the equator, the air cools and descends. Welcome to the subtropical high-pressure belt. This belt encircles the Earth, lying roughly between 20 and 35 degrees latitude in both hemispheres. Here, the air, having shed its moisture while rising at the equator, descends, becoming warmer and creating areas of high pressure. One of the most striking effects of this high-pressure system is its ability to create deserts. Think of the Sahara in Africa or the Australian outback. These aren't just coincidences, they are directly influenced by the subtropical high-pressure belt, which limits the formation of clouds and precipitation, allowing for arid climates. Moving on to the Ferrel cell, which operates in the mid-latitudes. It's a bit more complex in its workings. Air in the Ferrel cell flows poleward and eastward near the surface, but it takes a turn equatorward and westward at higher altitudes. This cell acts as a mediator between the cold polar air and the warm tropical air, crucial for the temperate climates we experience. This belt and cell are crucial for understanding weather in temperate regions. But what happens as we go even further? Closer to the poles, the plot thickens with the subpolar low-pressure belt. Nestled between the chilly polar regions and the warmer mid-latitudes, this belt wraps around the Earth like a stormy sash. Here, the atmosphere is a bustling hub of low pressure, a key player in shaping the weather patterns that define these latitudes. The subpolar low-pressure belt is notorious for its role in generating some of the most dynamic and wet weather on the planet. This belt is where cold polar air meets the warmer air from the south, leading to frequent storm formation. These storms are not just local phenomena, they can have far-reaching effects influencing weather patterns across the globe. Enter the polar cell, a critical component of our planet's atmospheric circulation. Over the poles, air cools dramatically and sinks, creating high-pressure areas. This dense, cold air then flows outward towards lower latitudes at the surface, completing the cycle of the polar cell. This continuous flow not only helps regulate the Earth's temperature, but also plays a pivotal role in distributing energy and moisture across the planet. These areas might be cold, but their impact on global climate is anything but negligible. All right, let's tie all these atmospheric threads together. We journeyed from the steamy equatorial low-pressure belt, where warm air rises due to intense solar heat, creating a zone ripe for thunderstorms and heavy rainfall. This is the engine room of the Hadley cell, which pushes this warm, moist air toward the subtropics. Moving on, we met the subtropical high-pressure belt, a region where this air, now cooler and drier, descends, fostering arid deserts in places like the Sahara and the Australian outback. Here, the feral cell takes over, circulating air between the high-pressure subtropics and the cooler subpolar lows. Speaking of which, the subpolar low-pressure belt, with its tumultuous weather, is vital in driving the moist, maritime climate of regions like the British Isles and Pacific Northwest. This is the playground of the polar cell, which completes the atmospheric loop, chillingly pulling air down from the poles and heating it again as it travels equatorward. These belts and cells are not just isolated phenomena, but are deeply interconnected, influencing weather patterns and climates across the globe. Next time you experience a particularly hot day or a sudden rainstorm, remember these invisible forces at play. Thanks for tuning in.